We present our work, Octree-guided unoriented surface reconstruction. We address the problem of surface reconstruction from unoriented point clouds using implicit neural representations, or INRs. In order to avoid bad local minima which gradient descent easily gets stuck in for this task, we propose a two-step approach, OG-INR, where we first construct a discrete octree and label what is inside or outside, and then optimize an INR guided by the octree's labeling. To solve for the labeling, we propose an energy function and an efficient move-making algorithm that explores many possible labelings. Our results show that the exploration by the move-making algorithm avoids many bad local minima reached by the purely gradient descent-based methods. We consider the surface reconstruction from point cloud task, where we have no information relating to the inside or outside of the shape. So we have no occupancy information, no SDF information, no surface normals, and no line of sight information. However, we assume that the object is watertight and completely within the domain of reconstruction. Implicit neural representations, or INRs, have been shown to give good results on the task when inside-outside information is available. Given an input point cloud chi, they optimize an INR phi to regress the sign distance field, or SDF, to the shape, using the following losses. The zero-level set loss enforces that there should be zero SDF at the input points. The icono loss enforces that the gradient norm of the network should be 1. The SDF loss tells the network to match the known or estimated SDF values. And the normal loss tells the network's gradient to match the known or estimated normals. However, in our unoriented version of the task, we can only use the first two loss functions. This is a very underdetermined problem. The optimization thus relies on heuristics and regularizers to recover the surface, for example, geometric initialization or smoothness-based regularization. These methods are slow to converge and often get stuck in local minima. As an example of this, let us look at silent when trained without normals. The INR gets stuck due to not knowing whether points away from the surface should have positive or negative SDF. This causes large amounts of ghost geometry, as the INR can only adjust smoothly and cannot completely flip its sign. We can see this more clearly when training on 2D shapes. However, whether a region is inside or outside the shape should be obvious for some regions. For example, the outside convex hull of the input points should be outside the shape, and it requires complex reasoning for most other regions. We propose to do this outside of the INR, as INRs are bad at getting stuck in local minima and trying multiple possibilities. We now give an overview of our approach. Given an input point cloud, we first build an octree around the input points and label nodes as being on the inside, outside, or surface of the shape. We then train an INR using the labeled octree as guidance. When building the octree, we set any nodes containing input points as surface nodes, which are colored yellow. During the labeling step, non-surface nodes are labeled as either inside, which are colored blue, or outside, which we have made transparent. To label the octree, we propose an energy function that captures the surface reconstruction task. The first term encodes a surface property, while the second term encodes a minimal surface constraint. The surface property term encourages every surface node to be close to an inside or outside node. In practice, we only look at its direct neighbors, encourage a specific quota on the number of inside and outside neighbors, and count surface neighbors as a mixture of inside and outside. The minimal surface constraint encourages the surface area between nodes labeled as inside and nodes labeled as outside to be minimized. This energy function is non-trivial to minimize. In particular, it contains an n-ry term that is not concave, so we cannot use efficient methods for exact inference. Instead, we employ a move-making algorithm with moves specialized to the problem. To make it efficient, we constrain the move set and use a cause-to-fine approach. We only allow labels to change from inside to outside. We only change labels for nodes on the inside-outside border. We iteratively grow potential moves. And finally, we apply moves at multiple Octree depths before reaching the final depth. We now visualize the Octree labeling algorithm in 2D. At initialization, we set all nodes to inside, and then set the nodes on the boundary of the domain to outside. We then repeatedly label and expand the Octree. We also visualize our Octree labeling algorithm in 3D. We then train the INR using guidance from our labeled Octree. Our loss function is a combination of 4 loss terms. The first 2 terms are standard INR loss terms for the surface reconstruction task, the zero level set loss and the iconal loss as explained before. We introduce 2 losses based on information from the Octree. First, we approximate the SDF for points of the domain by approximating the distance to the surface as the distance to the input points, and using the labeled Octree to determine the sign. The first Octree loss enforces the predicted SDF to match this approximate SDF. For the second Octree guided loss, we sample a fixed number of samples from each Octree node and enforce that the sign of the predicted SDF matches the Octree. Note that this method of sampling automatically makes our samples to be denser, closer to the surface, due to the Octree structure. Note that we take surface nodes to be inside for both of the Octree guided losses. Finally, we only apply the Octree guided losses for the initial part of training, as they are approximate and guide the INR towards the correct SDF. Thus, our Octree labeling method can be seen as a good initialization method for the task, avoiding many local minima that gradient descent cannot avoid. As our method is not dependent on the INR, we show results on 2 vastly different INR architectures, Siren and NGLOD. Our results show that on synthetic and well-sampled data, we outperform previous INR methods on average on both our metrics, even if they use ground truth normals. When the input point cloud has many defects, such as misalignment and large missing regions, we are competitive with state-of-the-art methods. Because our Octree guidance quickly guides the INR to a rough solution, the INR training portion of our method needs much less iterations than previous methods. As a result, our entire method, building and training and labeling the Octree, as well as training the INR, is much faster on average than other recent methods. Here is a comparison of our method on shapes from the SRB and ShapeNet datasets.